Okay, this shouldn't take very long. There were some of you who had questions about why something of this, why this, why the computation of derivatives was dependent, how it was dependent on the singular values of the weight function. But there's specific people who asked me this question are not present over here, so I think I'll skip the question. Now, did everybody understand exactly what was happening until this slide? Question, folks? So Rohan, did things make sense until this slide?
Yeah.
Okay. What about the rest of you? Joshua, Minyang?
Yeah.
Okay, good, right? So the problem here was, so what were the problems we had? What was wrong with this framework?
The gradients would get really small because you kept multiplying it by a number less than 1.
Yeah, because the Jacobians were generally of a shrinking nature, and the weight matrices, most vectors shrink when multiplied by a weight matrix. So as a result, both going forward and going backward, the what was being remembered by the network would get forgotten going forward, and the derivatives would vanish going backwards, right? And so we wanted a network where we basically got rid of these nasty elements, the weights and the activations. So you wanted a network where what was in memory was only modified by patterns seen in the input. And so we came up with a structure, something we call the constant error carousel, which was just a memory that went through straight with no activations and no weights. So which means that there was no intrinsic reason for the memory to change as you went down time. Any changes were caused by external influences through these sigma terms, which are gating terms. And since the memory itself has no nonlinearity, we wanted to have some subsequent nonlinearity at each time, which modified what was in memory before passing it on. And of course, these gates had to be computed on the input. The hidden state, which is the non-linearly transformed version of what's in the memory, and other stuff, and possibly even what's in the raw memory itself. And this was what gave us the long short-term memory unit, where the idea is to explicitly latch information to prevent decay and blow up. So that gave us the structure over here. Here's your standard recurrent neural network unit in the hidden state, where the input and the previous hidden state value were together passed through an activation to give you the next hidden state. We modified this little unit for the hidden state by something far more complex, which looked like this. And so the RNN cell, which looks the LSTM cell, which looks fairly complex, when you go down to it, isn't that hard. The basic structure is this constant error carousel, which passes data in without passing it through any kind of weight function or any kind of a weight matrix or any kind of activation. So this was the CEC. And the way things got modified was through these external gates, which are sigmoidal units with outputs in the range 0, 1. And this controls how much of the information is to be let through. So you had different kinds of gates. The first gate was the so-called forget gate. Now, the example we used in class was a program that you were trying to analyze with curly braces. So if you had the memory unit said, I have 6 open curly braces, then you would want to decrement that count. But to decrement the count, you first have to detect that there's a closed curly brace. So the forget gate detects patterns that cause you to forget what is in memory. And the forget gate acts on patterns on the input, but also considers context, which is the previous hidden state and as we'll see later, also what's in raw memory. Then when you wanted to increment it, you wanted to say, okay, this thing's carrying open curly braces. Have I seen a new curly brace? That is the stan unit over here. This one simply determines if there's any pattern detected in the input that must increment what's in memory. But that is actually modified by this gate here. And this gate determines if whatever you have detected is relevant and must increment the memory. So again, going back to our example, if the main line is carrying the count of open curly braces, you want to say, yes, I've seen another curly brace, and no, it's not in a common section. And then if those two conditions are met, you're going to increment what's in memory. So here's what happens. So this is the forget gate. The forget gate is a sigmoidal activation that operates on the previous hidden state and the input. And then here you have the pattern detector, which operates on the input and the previous hidden state. And there's the input gate, which operates on the same two things to determine if the pattern that has been detected is relevant. And the actual update of the memory is like so. The memory before time t minus 1 is ct minus 1. It is first modified by the forget gate, which is multiplicative, to determine if it must be decremented. And then it's modified by the second term, which is the product of the pattern detector and the input gate to determine if it must be incremented. Now observe that these two operations are different, because if both of these operations were identical, if both of them were plus, then it's both of them it becomes symmetric. And so you wouldn't actually have the explicit ability to modify, to decrement and increment as separate operations. So these two operations had to be two different operations. Forgetting had to be a multiplicative, incrementing had to be additive. And then finally, of course, what's in memory must be modified through a nonlinear process. So that is put through a tanh activation. We use tanh because, as we saw, tanh have the best memory response structure, and you would like to see some of the carryover even in this hidden state. And the output of this nonlinear transformation is also modified through a gate called the output gate. Now, just to make sure that these gates operate on all available information, you don't just operate on the input and the previous hidden state, but also on the what's in the raw memory itself. And so this is called the peephole connection. CT minus 1, which establishes past context, is used to is used in the computation of both the forget gate and the input gate. And it's not used in the pattern detector. This is only for, the gates, whether things must be forgotten and whether the context is just right. And then after the memory is updated, the updated memory is used for the output gate, which modifies the non-linearly transformed version of the memory. So here's the complete unit structure with input, output, this input, this forget gate, input gate, output gate, input pattern detector, and the output nonlinear transformation, where all of the gates use all available information, including the input, the previous hidden state, and what's in raw memory. Now observe that the structure is different from a standard recurrent neural network structure. In a standard recurrent neural network unit, you had one line coming in and one line going out. Here you have two lines coming in. One is the raw memory itself. There's a non-linearly transformed version of the memory. And you have two lines going out, the raw memory going out, and the non-linearly transformed version of the raw memory. Now, these are describing the horizontal connections across time. What about vertical connections across layers? Across layers, only this HT, the non-linearly transformed version, is going up. And only this is going to go to the next layer of the network, which could also be an LSTM connection. So here's what we had. We saw this pole, right? In the class. Now, here's the complete computation. Yes, Vibha, what's the question?
I just had a quick question about this diagram. I was a little confused. So the line that depicts xt as well as h of t minus 1, both of them join. So I wanted to understand if that's like an additive operation
That's
or...
just a concatenation, like I have over here,
Okay, got it.
right? That's just a concatenation. Simplifying the figure, that's all, right? Okay, so here is the complete set of operations. At any time, the previous raw memory comes in, you get the current input, you first compute the forget gate. Then you go on and you compute the input gate, and you also compute the input pattern detector. Then once these three have been computed, you can update the raw memory, where the raw memory is multiplied by what's in the forget gate, and then you additively combine the product of the output of the pattern detector and the input gate. Now here you have the updated memory, which is going out CT. The updated memory and the current input and the previous state context is now used to compute the forget gate. And the updated memory is modified using the tanh nonlinearity, and this non-linearly transformed memory is scaled by the output of the forget gate, and that product becomes the actual non-linearly transformed state. So here is the complete sequence of operations. First, you compute FT, forget gate. You compute the input pattern detector. You compute the input gate. All of these three are used to update the memory. Now, the updated memory and the input in HT are used to compute the output gate, and the final output HT is the non-linearly transformed raw memory times the output gate. So, simple operation. But then if you want to write this as code, you probably want to write this as an object-oriented routine. You'd write something called an LSTM cell. And the LSTM cell is going to take in, now consider the inputs, right? The cell takes in the previous raw memory, the previous hidden state, and the current input. It outputs the next raw memory and the next hidden state. So that's what the cell will do. It's going to take in the raw memory, the hidden state, and input and parameters. Its output going to output the raw memory and the hidden state. So the actual code, this is just the sequence of operations within the cell itself. It's just the equations that I've presented earlier in serial format. I won't actually go through it. But then when I'm computing the actual recurrent network, this looks just like your standard RNN, right? You go through time. At each time, you initialize your hidden state, the 0th layer hidden state as the input itself. Then you go through the layers, and within each layer, I'm assuming that every layer has, all layers are LSTM cells. The LSTM cell is going to take the raw memory and the hidden state to the left of it, the hidden state below it, and is going to output the raw memory and the hidden state for that time, right? So you just loop through this, and when you're finally done with all of the layers, the final output, which is the hidden state, is used to compute the output. So easy. Now, this code, this sequence of operations looks very complicated, right? And so when we try to train something, backpropagating derivatives is going to become very painful, because now we're going to have to backpropagate the derivatives through an entire LSTM cell. Again, the training is just like a regular RNN. You define a sequence divergence and backpropagate the derivatives. The problem is the backpropagation through the cell. And so if I take a look at 2-time instance, let's look at the derivatives here, right? this derivative is going to get a contribution from this line, but also from this line, and then from this line, and then from this line, and then from this line, right? All of the, if I simply look at the influences, there are so many different influences when I want to compute the derivative of the divergence with respect to CT. And then I also have this guy. So you can keep writing equations, and writing equations is not going to be easy at all because there are so many complicated influences. Same thing. If I'm trying to compute the derivative for HT, the derivative, you have a derivative coming from up here. You have a derivative coming this way. You have another coming this way. You have yet another coming this way. I can keep drawing things, right? And so as you can see, writing derivative equations for backpropagation is going to be a very fruitless exercise. And so trying to explicitly write out all the formulae for backpropagation can be tedious and very painful, simply because every variable has so many direct and indirect influences. So how do you do backprop over here? We are not going to explicitly derive the derivatives with respect to weights. What we will do is to look at it through code where we break things down, okay? I'm going to sort of quickly zip through this, but we have a very nice handout on how to compute derivatives for very complicated functions, which will be handing out at the and will be put up on the course page today or tomorrow, right? But first, to see how you can compute a derivative, let's look at all of the equations going forward, right? In the forward, the C and the H from the previous time and the X from the current time come in, and you get C output and H output, right? And the sequence of operations is like so. First, you compute the affine term for the forget gate, put it through the sigmoid, and compute the forget gate. Then you compute the affine term for the input gate, put it through the sigmoid, compute the input gate. Then you compute the affine term for the pattern detector, put it through the tan H, you compute the pattern. Then the output raw memory is the forget gate value times the input raw memory, plus the input gate value times the output of the pattern detector. Then you compute the affine term for the output gate, put it through the sigmoid, you compute the output gate, and then finally the hidden state that goes out is what's in the raw memory put through a tan H, and then multiplied by the output gate. So this sequence of operations making sense to everybody? Over here?
Yep.
Yeah, so what will happen when I'm computing derivatives backward? What do you think I will begin with, and what will I end up with? Anyone?
You'll start from the bottom.
So what is going to be here? If I just look at the top level, what derivatives will come in and what derivatives will go out?
I think the derivative with respect to C and H would come in because they're the output.
So the derivative with respect to CO and HO would come in, and the derivatives
And
with
we,
respect to C, H, and X would go out, correct?
yeah.
Going forward, these were the inputs and these were the outputs. Going backward, you'd have derivatives with respect to these come in and derivatives with respect to these go out. And these derivatives are going to be computed going backwards, right? So here's what the derivative code is going to look like. I'm going to have the derivative with respect to CO and HO. And I'm setting all the other variables in also because you need to compute the derivatives at the current position, right? And the output is going to be the derivatives with respect to C, with respect to H, and with respect to X, which are the terms that went into the forward, and also the derivatives with respect to the parameters. So the last operation over here was HO was O times tan H of CO, right? Now the derivative for CO came in. So DO is simply going to be, again, if H equals O times tan, right? So DO is going to be DH times tan. And d tan h is going to be dh times O. Do you see how that happens here?
Could you repeat that, Professor?
So I have h equals O times, let me just call this t, this entire variable, right? H equals O times t, correct? So if then that means that the derivative for O, dO, is going to be dH times t, correct? When I say dH, it's a derivative of the loss with respect to h. So going backwards, if I have the derivative of the loss with respect to h, then the derivative for O is going to be the derivative of the loss with respect to h times t, right?
I guess. Yeah. Okay. Yeah.
Let me explain it with let me just put a new slide, right? If I say h equals O times t, right? If I give you dH, then dO equals dH times t, correct? dt equals dH times O. Sorry, dH times O.
Would it not be so? I think like intuitively, my mind's saying it's d. If you know dh, then do is dh divided by t. But is that
But
not?
wait, these are derivatives. So it's dl over dh. So I'm going to say dl,
Okay. Yeah.
correct? I'm just using that short notation, right? Does that make sense?
Yeah. Yeah. It makes sense.
Everybody, does this make sense?
Yes.
Yeah.
Right? We are just going to be using this rule again and again and again. So here's what it is, right? This was the forward equation. When I go back, the first thing was I'm inverting h equals O times tan, right? So if I'm inverting this guy, let me see if I can get a laser pointer. If I'm inverting this guy, then I'm going to get dO equals dH times tan, right? And d tan is going to be dH times O. So do you see how these first two equations hold?
Yeah.
Right? But then I have the derivative for this entire variable tan h, right? So if I have the derivative for this whole thing, then I can say dc equals d tan times 1 minus, if I say y equals tan h of c, right? If I have dl over dy, then dl over dc is going to be dl over dy times 1 minus tan square. This is just a standard formula for the derivative of tan h. Did this make sense? If it didn't, let me actually write that again for you. I have this here. I can say t equals, sorry, tan h of c, correct? So this means I'm given dl over dt. This implies, what is dl over dc?
dl dt by dt.
It's the derivative of tan h, correct?
Yeah.
It's going to be dl over dt times tan h prime of c, correct?
Yeah.
Is this right, guys?
Yep.
Right. So that's basically what this formula is doing over here. This formula is just it's dl over this d tan h c0 is simply this derivative term times f prime of tan, the derivative of tan h, which is this guy. So do you see how this equation came about?
Yeah. But why is it transposed for both this one and
These
dl?
are all vectors and matrices, so that's why. that this is for keeping the shapes.
Okay.
You'll have to work out the shapes later on, but the general formula, we have to make sure that all the shapes match, right? The derivatives need to have specific shapes. That's where the tan H comes in. I'll leave you to figure that out on your own. But the general formula makes sense, does it not?
Yeah.
AG, Rohan, Josh, makes sense?
It makes sense.
Yeah.
Yeah.
So you can see how I took this complicated thing and I simply inverted it. Now, this was the last operation here. So the next derivative I'm going to compute is for this next one, right? Which is O equals sigmoid Z0. I have the derivative for O. So the derivative for Z is simply going to be the derivative for O times the derivative for the sigmoid, right? Same formula.
Yeah, makes sense.
Guys, is this making sense?
Yeah.
Right. Now going back, the previous operation was this one, correct? So I need to compute the derivative for this one. Now observe that I keep using plus equals, right? That's because variables are being reused. But then if I go back, at this point, I already have the derivative for ZO. So because I have the derivative for ZO, now I can go back and say, update my derivative for CO and say derivative for CO plus equals DZO times W. The derivative for H is going to be DZO times WOH. The derivative for X is going to be DZO times WOX. The derivative for BO is simply going to be the derivative of 0, correct?
Yeah.
And similarly, the derivative for WOC is going to be DC times DZO, and so on. I can simply just invert this and compute the derivatives for all the terms on the right based on the derivative for the term to the left. This makes sense, guys?
Yeah.
Yes.
Right? And so we've gone past this guy. The next one to go past is this guy here, right? I'm going to use the same mechanism because now I have the derivative with respect to CO. I can go back and compute the derivatives for each of these terms, right? Make sense?
Yeah.
Yeah. And now I can go back and compute the derivative for this one. And so that's going to be this formula. And now I have DZC. So then I can go back and compute the derivatives for all the terms on the right for the equation that immediately preceded this guy in the forward pass, which are the derivatives for all of these 7 terms on the right. That makes sense, guys?
Yep.
Yeah.
Josh, Rohan,
Yeah.
AG, yeah, right? And so we've gone up here, and then I can keep going back this way, right? And the rules are really very simple at this point. When I keep writing derivatives, I can just keep inverting one equation at a time, going backwards, until eventually I get the derivatives for all the terms that went into the network and went into the cell. This makes sense?
Yep.
Right?
Yep.
And so I can just, this was the forward equation, right? Now in the backward equation, I'm just going to start from the end and go backward in time. And then I'm going to start at the final layer and go to the first layer. And I'm just going to, for each cell, I know how to compute the passing the derivatives for the outputs and compute the derivatives for the inputs. So I can just plug that into the formula. There's one little thing here. And the output of each cell went both right and above, right? So when you look at the derivative for, when you went forward, sorry, the C, this hidden state went to the right and then went up to the next layer. So when you go backwards, the derivative dH over here should actually sum terms from above and to the right. So that's what this little guy is doing. It's summing derivatives from the right and above, okay? But other than that, it's just literally plugging in this derivative routine that we wrote over here into the backward loop. and thus the entire back propagation can be performed. Again, I'm not going into the details of the formula, but the general logic makes sense.
Yeah.
Josh, Vibha, AG.
Yep.
Right. Okay, so, okay. Outside, this makes sense? Okay, yeah. Anyways. And so that's it. We know how to perform backprop. One last topic was, do we really need things to be this as complex as the LSTM? This is a pretty complicated thing, right? So this is unit here. Can we simplify it? And so there have been various attempts at trying to simplify it. One of them is the GRU. And LSTM may be unnecessarily complex, too many equations, so the GRU tries to simplify things. It assumes that, you know, if I'm seeing a curly brace, I'm not closed curly brace, I'm not seeing an open curly brace. Things like that. So it combines forget and input gates. If the input must be incremented, it doesn't have to be decremented. If an input is going to be decremented, then the memory line does not have to be incremented. So you use a single gate, and whatever value goes to the right here, 1 minus that goes up here. So you combine the input and forget gates. Another thing is, in your standard LSTM cell, there were 2 lines going up. You had the raw memory, and then you had the non-linearly transformed version of the raw memory, both going out. Why? Just have the raw memory go out and perform the nonlinear transformations inside the cell. So 2 simple modifications, and that gives you the GRU, right? So, and then there have been various other modifications. Now to close out, when you have a recurrent network, now the structure remains the same as before, except now that these green boxes are going to be LSTM or GRU cells, right? Again, remember that each of these boxes is actually an array of units, but you can think of it as a vector operation, right? And you can use the same things in bidirectional networks as well, except now the hidden nodes are LSTM units. And so, to close out, recurrent networks are poor at memorization because memory can explode or vanish depending on the weights and activation. That's the memory going forward. Going backward, they also suffer from the vanishing gradient problem. And as a result, error at any time cannot affect parameter updates in the too distant past. So LSTMs are an alternative formalism where memory is made more directly dependent on the input rather than network parameters through a constant error carousel structure, which has no weights or activations, but instead uses direct switching and increment-decrement operators. These do not suffer from the vanishing gradient problem, but they actually do suffer from the exploding gradient problem because things can accumulate. So that's the end of today's lecture. There's some issues to deal with. How do you compute divergences between sequences? How do you use these networks? This and more we will see in the next couple of classes. I'll stop the recording here.